Okay, so we're going to be looking at this topic, vertical motion under gravity today. Quite an interesting one. The idea is you've got these SUVAT equations, these five equations, which relate five quantities of any scenario. You know, the total time, initial final velocity, the displacement, total displacement, and the acceleration, the constant acceleration. And this is really useful for describing and modeling objects which are falling or objects which are about to fall, anything that experiences gravity, which is useful because if you're near the surface of the Earth, you tend to experience gravity. And the other reason it's useful is because we can model it as being constant. And we'll talk about that in a later slide. But near the surface of the Earth, we can model gravity as being a constant force. So to just start off with classic questions, you know, these are 100 years old questions, but I want you to just think about them and most importantly, explain why, right? And I'm not necessarily even asking which hits the ground first. I'm asking a more fundamental question. Which one has the faster acceleration? A bowling ball and a golf ball, when I drop them, do they accelerate the same or do they have different accelerations? And likewise, bowling ball and a feather, do they have different accelerations? And I'm talking on Earth, you're doing it, or well, I said I was doing it, but it doesn't really matter. A normal person on Earth just dropping these two items, so no sort of strange scenarios, sort of real world scenario, what would the accelerations be? So have a think and see if you can explain why. You can pause now. Okay, and the answer is in the first case, hopefully we agree, same acceleration. Same acceleration, they will in fact hit the ground at the same time because they both started at zero speed. They accelerated at the same constant rate. They therefore hit the ground at the same time. And in the case of two, bowling ball accelerates faster. And then the key question of why would the bowling ball accelerate faster than the feather? What is the key difference between these scenarios? And in this case, real world, it's air resistance, right? So air resistance ruins it. It ruins this nice little rule that we have, which is that all objects, you know, hit the ground at the same time. And in a simple universe, this is the case. But if you complicate things with air resistance, then your experience tells you it isn't the case. But you should see that more as an exception to a more general rule. So feathers are commonly used in these examples because they provide an obvious exception to the rule, right? It doesn't hit the ground at the same time as the other two. The reason, though, isn't because of anything to do with gravity so much. It's because air resistance is extremely or has a very large effect when you're using something like a feather, which is very light and has a surface area that is conducive to causing a large air resistance. Not so the case with a bowling ball and a golf ball. So just because it's actually quite relevant to the question I just asked, I'm going to splice in here a video that was taken I think a few decades ago, maybe 70s, late 60s. I forget the year exactly, or did I note it down? No, I didn't. So a few decades ago, a few people were on the moon and they did this experiment effectively. I think it was their last day, and just before they left, as an experiment, having spent, you know, billions of dollars to get themselves to the moon, they thought it was worth the time to just try this out. So almost like the example I just described, a hammer and a feather on the moon, which one hits the ground first? Let's take a look.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
So as you saw, in that case, the acceleration was in fact the same, right? They both hit the ground at the same time. The acceleration is the same. Why does it make a difference if you're on the moon rather than Earth? Just to make it absolutely clear, it has nothing to do with the gravity being different or weaker. It's because there's no air resistance, right? The moon, well, I suppose you could argue because of its weaker gravity, and this is getting slightly out of my area of expertise, ultimately the moon doesn't have an atmosphere in the way the Earth does, which is bad for the humans on it, but it's good for demonstrating the fact that objects do in fact accelerate at the same rate if you remove the air resistance. They fell a bit more slowly because the gravity is weaker, but it doesn't matter. The point is the acceleration being constant when the air resistance is gone. So let's just talk a bit more about this acceleration, but let's bring it back to Earth. So there's this constant that's going to be coming up constant. Oh, that was not intentional. There's a constant we're going to be using a lot, which is 9.81. I'm just going to write it now so you can start remembering it while I talk. In fact, and let me make it clear, we will use 9.8. Okay, so we don't have time to get into the details of, why gravity exists or how exactly gravity works. That'll be more for physics, or if you did mechanics at further maths. But what we can say is this: when you're near the surface of the Earth, the acceleration that an object experiences because of the existence of gravity is 9.8 meters per second squared downwards, right? That's the acceleration it experiences. So if I have, let's say the bowling ball, I'll make up some numbers. Let's say that's 5 kilos, and let's say the smaller golf ball is 1 kilo. In both cases, the acceleration downwards is 9.81. Right, I'm using the double-headed arrow. It's 9.81. I'm going to start using 9.8 more, just because within the exam, 9.8 is the number you're going to be using. It's just rounded. Now, if you think about what that means in terms of forces, it's as follows. Remember F equals ma, so both these objects are falling. F equals ma should always apply. If the mass for this one is 5 and the acceleration is 9.8, then that's going to be RF, right? What we tend to do is, rather than write 9.8, we're just going to use the letter G, right? G for gravitational constant. So what we'll do is, we'll label it as a force downwards, and this green arrow is a force, of 5G. And this is the weight force, okay? And in the case of the object that's 1 kilo, its mass is 1 times 9.8, and that's its force. It's just 1G, right? So the force on this object is 1G, and again that's its weight, and it's a force. It's the weight force. Okay. So effectively, what I'm saying is, for a given object, if you change its mass, if the mass increases, then the weight force increases, and that all balances out to mean that overall the acceleration is always the same. Okay, so between these two pictures, right, these two different scenarios in blue, they have different masses, they have different weights, but they have the same acceleration. So that's what you want to keep in mind. When two objects are falling and they're falling at the same speed, they may have different forces acting on them, but their acceleration is the same. Okay, and then just to wrap up a couple of things to make it completely clear, Mass is a property of the object, whereas weight is the force acting on it. The weight is always mass times g. So from now on, whenever you hear about the mass of an object, just think, oh, its weight is that times g, right? A 10 kilogram object has a weight of 10 g. And don't get confused with grams either. It doesn't mean 10 grams, it means 10 times 9.8. An object of mass 25 kilograms has a weight of 25 g. It has an acceleration of g. Everything has an acceleration of g. Okay, so now that we know this, that we know that objects near the surface of Earth, when they fall, have this acceleration of g, 9.8, we can start using it in SUVAT. So we're going to do another series of learn by example. I'll go through 4 examples. The earlier ones will be simpler, and then you'll be able to do some questions. Okay, and this should hopefully cover enough different scenarios that you get comfortable with using SUVAT with gravitational constants. Okay, so a book falls off the top shelf of a bookcase. The shelf is 1.4 meters above a wooden floor. Find the time the book takes to reach the floor, the speed with which the book strikes the floor. Okay, let's divide that up into A and B. I don't know why it matters that the floor is wooden. I guess it's just trying to paint a more exciting picture for us. But here's the information we've been given. It's 1.4 meters above in each case. The book falls, so it just starts falling. So let's start doing SUVAT. For A, what do I know? So the initial speed is 0. The time taken is the thing I want to know. The distance is 1.4. The v, the final speed, I don't know in this case, but the acceleration I do know. And we want to be careful how we put this down. So first of all, when I said s is 1.4, what that means is I'm taking down as being the positive direction, right? Because I'm saying it started at 0 displacement, and if by the time it hits the floor it's at 1.4 displacement, that means it increases when I go down. The alternative would be if I said it was at minus 1.4, which means I'm saying I'm taking up as positive. So it's up to you which direction you treat as positive. You could say s is 1.4 or s is minus 1.4. It doesn't matter. As long as you're consistent, you'll still get the same correct answer, because your other variables, for instance A, is going to end up being the same or opposite sign accordingly, right? So let's pick it as downwards, and then very importantly on our diagram, let's indicate, maybe not in green, let's indicate we're taking down as positive, and I tend to just write it this way. Do an arrow and then put the positive, plus VE to mean positive. So down is positive. What's our acceleration then? It's g, right? Acceleration is g, which is 9.8. Okay. So now it's just a case of use the correct SUVAT equation. We've got S, U, A, and T. We pick the one and only SUVAT equation that has all 4 of those, which in this case is S equals UT plus half AT squared. So I end up with 1.4 equals 0 times a half A, which is 4.9 T squared. And if you solve that, you should get a T of 0.5345, right? It's 1.4 over 4.9 square rooted. And that's it. So that's how many seconds it takes the book to hit the ground. It takes 0.45345 seconds. For then the B case, it's SUVAT again, as it will be in all cases, but what's changed? What's changed is I'm not interested in time anymore. I'm interested in the speed with which the book strikes the floor, so that's V. So my V is my unknown. So my suvat equation then is going to be v squared equals u squared plus 2as. V squared therefore equals 0 plus 2 times 9.8 is 19.6 times 1.4. So V is basically going to be the square root of that. In this case, that ends up being the square root of 27.44, which is 5.238 meters per second. Fairly fast. Okay, that's it. It's just suvat again, but this time your acceleration is taking a value of 9.8. So before we look at this next example, I just want you to think about the following situation of throwing an object in the air and then eventually it lands on the ground. So if I'm standing here and I throw my object, whatever it may be, and it goes up in the air, I throw a tennis ball, something not too heavy, it goes up and oops, and it goes like this. Okay, so this is projectile motion, and we're actually not going to look at this quite yet, but we're going to look at a simpler case for which I then want to think about the velocity at the highest point, right? So at the highest point here, it's going to be going at some speed, right? I'm throwing it, it's here at the highest point, and it's got some sort of horizontal speed, effectively. But now, let's think about the simpler case where you just throw an object directly up in the air, right? So it goes up in the air, and then eventually it falls down again, okay? Those up and down lines should be coinciding, really, okay? So if I just draw what that looks like, you've experienced throwing things up in the air. This is what it roughly looks like. It goes up, it slows down, and then it falls back down again. When it hits the highest point, how fast is it going? So unlike the sideways throw, if I throw something directly up in the air, when it reaches the highest point, it will instantaneously have no speed, have a velocity of 0. Right? V equals 0 at the highest point. So this is a really useful thing to keep in mind, because what it means is if you want to know how high an object ends up going when you throw it in the air, all you need to do is ask, well, what is the displacement when the velocity is 0? And then you can use suvat equations. So this slide is mainly to just make you remember the following. An object at its highest point, if thrown vertically, will have a velocity of 0 instantaneously. Right, so it only happens for a microsecond. It's got this velocity of 0. After that, it starts falling down. So let's use this in the next example. A ball is projected vertically from a point X, which is 7 meters above the ground, with speed 21 meters per second. Okay. I'm going to take up as positive this time, just to make this clear. Also, let's skip part B because I've got a couple more examples to do. And I think it should be clear how to do that if you can do A. So a ball is projected vertically upwards from a point X, which is 7 meters above the ground, with speed 21 meters per second. Find the greatest height above the ground reached by the ball. Okay, this 7 meters above the ground thing is a little bit annoying, but it's not too difficult to sort out. If I just have a visual, so we're 7 meters above ground somehow. Okay, say we're on a hill, and we're then gonna figure out what is this, this greatest height. What is this point here? Okay, so what we're gonna do is let's forget about the 7 meters for a moment and just pretend that this is 0 rather than 7, and then this greatest height, this is going to be the S that I want to find out, right? So effectively, this greatest height is my value S. Right, I should say it that way, really. Okay, the total displacement is S. What will the greatest height be? So then let's use suvat. our initial speed is 12 going upwards. What is our final velocity that I'm interested in? It's going to be 0. That's when the max displacement is obtained, right? The S is the thing I'm interested in. T I don't know. What about acceleration? And we've got to be careful here. It is 9.8, but it's negative 9.8. Right, and the reason it's negative is because I said take up as positive, and as we know, gravity always acts downwards. So therefore the acceleration is minus 9.8, right? It's 9.8 going downwards. If I had taken, let's make this clear, that's taking it positive, right? If I had instead chosen to take down as positive, how would that change my SUVAT numbers? Well, my V would still be 0, because negative 0 is 0. However, my U, my initial speed, would now be minus 12. My S is still something I want to find out, and my A is now 9.8. So can you see how, depending on the direction that you pick as positive, some of your numbers will be negative, some will be positive, but it doesn't matter, because both of these will still end up giving me the same correct S value. Right? It'll either be positive or negative according to my interpretation of which way is up and which way is down, I suppose. Okay, so what is the greatest height obtained? We'll use SUVAT. I've got U, V, S and A. I'm going to use V squared equals U squared plus 2AS. Let's go with this version. Therefore 0 equals 12 squared plus, in this case, minus 19.6, which is 2A times S. Therefore S is equal to 144 divided by 19.6. Oh, sorry, did I write 12? Oops. The question says 21. Oh dear, classic. So it's 21. 21 squared is 20 times 22 plus 1, 441 over 19.6 is 22.5. Oh, I can't write on my face. 22.5, there it is. Okay, but is that the final answer? Be careful, because it says what's the greatest height above the ground. The ground is technically here, not here. So it's this black arrow here, double arrow, is 22.5, but then you've got an extra distance of 7. So the actual final answer is going to be 29.5 meters in this case. Yeah. So you want to just be aware that if your initial displacement is already not 0, then just call it 0, find the answer, and add on that number that it actually was at the end. Always just draw a diagram if you can't quite visualize the situation in your head. Okay, if you, for part B, if you wanted to find the time of flight of the ball, all you would have to do would be to say, now my T is my unknown, and I guess I should just mention this. If I wanted to find the time of flight of the ball, what would my S be? Right? If an object starts here and then it ends back at the same place again, what would S be? Should just be 0, right? So if you were answering part B, you would have an S of 0, and your V would be unknown. Cool. Okay, let's look at this one. A particle is projected vertically upwards from a point O with speed u meters per second. So it's going upwards with u meters per second. I'm going to take up as positive. The greatest height reached by the particle is 62.5 meters above. Okay, so this is the greatest height up here, 62.5. And that's when the velocity is 0. Find the value of u and the total time for which the particle is 50 meters or above u. Okay, that's a bit trickier. Right, let's find the value of u first. So we're going to use a displacement of 62.5. Velocity is going to be 0. The initial speed is what I'm trying to find, and my acceleration is minus 9.8. V squared equals u squared plus 2as. 0 equals u squared minus 19.6 times 62.5. That implies u is equal to, in this case, it turns out to be exactly 35. So you know your exam technique, you know it's working when your decimals cancel out to make a whole number. Okay, so 19.6 times 62.5 square rooted is just 35. Okay, so let's just write that in here, and then let's get rid of the working. So that was the initial speed. I think part B is the trickier question. So it's asking us, for how long was this particle above 50 meters or more? So if you imagine us adding another line here, about there, okay, and that's 50 meters, and what the object effectively does is this. It starts there, it gets thrown in the air, that's its maximum height, and then it comes back down. And the question is, when it first hit 50, for how long was it then above that height, right? So it's kind of like you've cut off the beginning and end of the full motion. So we can still use SUVAT for this, we just have to be a bit more clever. What we're going to do is we're going to find the two timestamps, right, the two values of t at which it hit the 50 mark. So let's say it's going up, and we're going to call that t1, so that's the first time it happened. Who knows when that is, maybe 5 seconds, 10 seconds, some value of t. Then it keeps going, and it comes back down, and we're going to get another value of t. Call it, say, t2, right, which will be a higher number. Find the difference between those two t values, and you'll get your duration of how long it was above 50. So to do that, SUVAT will actually do the work for us. We're basically saying, I want to know what t is for what when s is 50. And it's actually going to give us two answers, and we'll see why in a moment. Then just put the other things you know. I know that the initial speed was 35. V we don't know because we know it's 0 at 62.5, but we don't know what it is when s is 50. So forget V, we don't know. What else do we know? We still know the acceleration is minus 9.8. Okay, so we can then get our SUVAT equation, s equals ut plus a half at squared, which gives us 50 equals 35t minus 4.9 t squared. Or if I rearrange that to make it look a bit more like a normal quadratic, we got 4.9 t squared minus 35t plus 50 equals 0. Apparent, is that correct? Yeah, that's it. So then it's just a quadratic. It's not a nice one, so you can either use quadratic formula or you can use calculator. Solving the quadratic isn't the skill we're interested in learning today. We should know how to do that. You're going to get two t values, right? And they are, if we just take a look, in this case, one of them is 5.1686 and the other is 1.9742. I think it's more natural to call T1 the smaller one and T2 the bigger one, because T1 should occur first and T2 occurs second. So the object was thrown in the air. At 1.9 seconds, it hit here. Then it kept going up, and then it started coming down again. And now at this point, it's been 5 seconds, 5.1 seconds since it left, my hand or wherever, and then it starts falling down. Okay, so SUVAT does all the work for us. It found us both t values in the form of a quadratic. Find the difference between those two, and we have our final answer. So our final answer, let's write it here, it's going to be t2 minus t1 gives us the duration, which turns out to be 3.194 seconds. Okay, So that's the answer, 3.194. The object was above the 50-meter mark for just over 3 seconds. Good to know. Let's look at our final example. Okay, I just said let's look at our final example, but I've mercifully decided, actually I think I'll save it for a second part. I started explaining the example and realised there's actually quite a bit that you need to understand well. So rather than rush it, let's just do some questions which are relevant to those we've covered already, and we'll finish off the other example in a part 2 and get a bit more practice that way. So just 4 questions for you to try. They're all on this slide. See if you can give them a go. I think my face is just covering something here which says 4 marks. That last part, 11b, is 4 marks. And for the tip here, it says use v equals u plus at and substitute v equals a third u. That will make sense to you when you get to that question. Obviously, start from question 2 first. Okay, so give these a go. Let me know if you have any difficulty, and we'll do a part 2 next time. You can pause the video now.